But this is matrix multiplication. I'm going to quickly describe, in terms you're more familiar with, what's really going on here. Through an example, we'll take a function of two independent variables going in, two dependent variables coming out. E to the x cosine y, e to the minus 2x sine y. And we want to linearize around this point. X is 0, y is pi over 4. So we need the function value at that point. When we plug in 0, these will just be 1. So cosine and sine of pi over 4 is just square root of 2 over 2, square root of 2 over 2. So that's our function value, the first term in our linearization. But now we need a Jacobian matrix. And for that, so that would be a matrix of 2 rows, 2 columns. So for our first row, we're going to differentiate this function with respect to both x and y. So we're going to get e to the x cosine y and minus e to the x sine y. Then for the second row, we differentiate this function with respect to x and y. So we get minus 2 e to the minus 2x sine y. Then we have e to the minus 2x cosine y. But then we evaluate all these at this point, 0 pi over 4. So the matrix that we get ultimately that we're actually going to use is square root of 2 over 2 minus square root of 2 over 2 minus square root of 2 square root of 2 over 2. Now we can start running down the linearization, which is going to be a vector value function as well. So it's going to be the function value. So I'm just going to be using this formula right here. It's going to go all the way up here. So we're going to have this vector, square root of 2 over 2, square root of 2 over 2, plus that matrix where it's evaluated at the point. Square root of 2 over 2, 2, minus square root of 2, square root of 2 over 2, times the vector that shows a change in x and a change in y. So first a change in x, that's going to be x minus 0. Change in y, y minus pi over 4. Now, to complete this, we need to actually carry out the matrix multiplication. And the way we do that is, A is m by n. What I mean by that is m rows, n columns. And B is n by p. Again, n rows, p columns. These two have to match. Then C is A times B has m rows, p columns. And the way you compute that is the entry in row I, column J of C, and we'll step through this on this example in a second here, is the dot product of the ith row of A and the jth column of B. So that's how you carry out. So what's going to happen is here we're going to take the dot product of this row with this column to get the first component. Then we're going to take the dot product of this row with this same column to get the second element. So let's carry that out. So what we get is this vector from before, and then we're going to have square root of 2 over 2 times x minus 0 minus square root of 2 over 2 times this difference in y. And then for the second component, minus square root of 2 times x plus square root of 2 over 2 times the change in y. So then we can put it all together. So the first component function of the linearization is square root of 2 plus square root of 2 over 2x minus square root of 2 over 2 y minus pi over 4. And then square root of 2 over 2 minus square root of 2x over 2 y minus pi over 4. So this is your linearization. So here we have the partial derivatives multiplied by change in x here and change in y here, because these are partial derivatives with respect to x, these are partial derivatives with respect to y. So as far as describing linearization, you can describe it any way you want in terms of a summation of partial derivatives times change in the coordinates, or you can look at it from this matrix multiplication point of view, which is very similar to what we have in the single variable case. That's up to you. I wanted to show you the matrix point of view so you can see the similarities.